When you look up at the night sky on a clear evening, away from the blinding glow of city lights, you are staring into an ocean of infinite secrets. For generations, humanity has gazed at the twinkling points of light scattered across the darkness and asked a single, defining question. Are we alone in the universe? For a long time, this question belonged to the realm of philosophy, poetry, and science fiction. We imagined alien civilizations sending radio signals across the void or strange spacecraft visiting our world. But the reality of how we might actually find life in the cosmos is unfolding right now, and it is far more elegant than anyone anticipated. It does not involve spaceships or cosmic radio broadcasts. Instead, the answer is arriving in the form of silent, invisible beams of light traveling through the cold vacuum of space, carrying the microscopic chemical signatures of distant worlds. Imagine a planet floating in the deep shadow of space, more than 100 light-years away from Earth. It is a massive world, far larger than our home, wrapped in a thick alien atmosphere of hydrogen gas and surrounded by a vast global ocean of liquid water. This planet does not orbit a bright yellow star like our sun. Instead, it circles a small, faint reddish star that glows with a dim warmth. On this world, the conditions are profoundly different from anything we know. The gravity would pull heavily at your boots, and the air would be completely unbreathable to human lungs. Yet, deep within that thick atmospheric blanket, a delicate chemical dance is taking place. Molecules are colliding, reacting, and floating into space. Among these molecules are gases that, on our own planet, are intimately tied to the existence of living organisms. Could such an exotic and unfamiliar world actually be a better place for life to flourish than Earth itself? For decades, astronomers assumed that if we wanted to find life in the cosmos, we had to look for an exact twin of our own planet. We searched for rocky worlds of the exact same size, orbiting at the exact same distance from sun-like stars. We assumed that nature would follow the exact template that created us. But the universe is under no obligation to mimic Earth. The latest discoveries from our most advanced space observatories are shattering these old assumptions. They are forcing us to confront a startling possibility. The most common habitable environments in the galaxy might look completely alien to our experience. 1,000,000 miles from Earth, a massive space observatory is pointing its gold-coated mirrors toward the constellation Leo. It is capturing single photons of light that have been traveling through the cosmic dark for more than a century. By dissecting this ancient light, scientists are beginning to read the chemical fingerprints of alien skies. They are finding hints of water vapor, carbon dioxide, and methane. And buried deep within the data, they have spotted a faint, highly debated signal that has sparked an intense controversy across the scientific community. It is a molecular whisper that could represent the first tentative evidence of a living biosphere on another world. This is not a story of definitive announcements or sudden certainty. It is a story of real science in action, of a thrilling journey to the edge of the unknown, where every pixel of data is analyzed and debated. Prepare yourself. We are about to decode the skies of an alien world and take our very first steps into a much larger, living universe. To understand why an alien world over 100 light-years away has sparked such a massive scientific conversation, we first have to understand the immense difficulty of looking for life across the cosmos. For decades, the search for habitable environments outside our solar system was guided by a single, logical bias. We looked for planets that resembled our own. We assumed that because life evolved on a rocky world with a nitrogen and oxygen atmosphere orbiting a yellow star, nature must always follow this exact recipe. This narrow window of habitability meant that astronomers spent years searching for Earth twins, rocky spheres sitting in the comfortable zone where liquid water can exist on a solid surface. However, finding a small, rocky planet across interstellar space is one of the most frustrating challenges in modern science. Imagine trying to see a single speck of dust floating next to a blinding stadium floodlight from several kilometers away. The stars themselves are billions of times brighter than the tiny planets orbiting them. The immense glare washes out everything else, leaving the planets completely invisible to standard optical telescopes. Because of this limitation, the vast majority of the planets we have discovered so far are not small, rocky worlds like Earth. Instead, they are massive gas giants or intermediate planets that have no direct equivalent in our own solar system. This brings us to a strange planetary missing link a category of planets known as sub-Neptunes or super-Earths. These worlds are larger than Earth, but smaller than Neptune. In our solar system, there is a massive empty gap between the size of Earth and the size of the next largest planet, which is Uranus. But across the wider galaxy, this missing link is actually the most common type of planet in existence. For a long time, scientists did not know what these worlds looked like. They small, rocky cores wrapped in thick, suffocating layers of gas, making them completely hostile to life? Or could they be something else entirely, an entirely new class of habitable world that we never anticipated? This question led to the formulation of a groundbreaking scientific concept known as the Haitian world hypothesis. Researchers began to model these sub-Neptune planets mathematically and realized that their enormous mass could allow them to hold on to a very specific kind of atmosphere. Instead of an atmosphere dominated by heavy gases like nitrogen or carbon dioxide, these planets could be wrapped in vast, thick envelopes composed primarily of hydrogen gas. Underneath this deep hydrogen sky, the atmospheric pressure and heat could create the perfect conditions to support a global, deep ocean of liquid water that covers the entire planet from pole to pole. This hypothesis represents a radical shift in our understanding of where life can exist. A hydrogen-rich atmosphere acts as an incredibly powerful greenhouse blanket. It can trap heat so efficiently that a planet sitting far away from its host star or orbiting a dim, cool red dwarf star could still maintain liquid water on its surface. Furthermore, because these planets are significantly larger than Earth, their atmospheres extend much further out into space. This makes them much easier to see, analyze, and decode from incredible distances. But this discovery introduces a profound scientific problem. If we look at a planet covered in a global ocean beneath a thick hydrogen sky, how do we actually prove that something is alive down there? We cannot send a robotic probe to swim in those distant waters. The travel time alone would take hundreds of thousands of years using our fastest current technology. We cannot take a direct, clear photograph of the surface to see alien organisms swimming in the sea. The only tool we have is the light passing through the planet's sky. To solve this mystery, astronomers rely on a technique called transmission spectroscopy, which involves analyzing the behavior of light at an incredibly precise molecular level. When a planet passes directly in front of its parent star from our perspective on Earth, a tiny fraction of the starlight passes through the outer edges of the planet's atmosphere before traveling across space to reach our telescopes. The gases surrounding the planet are not completely transparent. Each individual chemical element and molecule absorbs very specific, unique wavelengths of light, leaving behind a distinct dark line or deficit in the spectrum. This means that an alien atmosphere leaves a permanent chemical fingerprint stamped onto the starlight. By breaking this light apart into its constituent wavelengths using highly sensitive infrared instruments, scientists can determine exactly what gases are present in that distant sky. They can look for water vapor, carbon dioxide, methane, and other compounds. However, the real challenge lies in distinguishing between ordinary planetary chemistry and the actual products of life. Many gases, such as methane or carbon dioxide, can be produced easily by completely non-biological processes. Volcanic eruptions, geological activity, and photochemical reactions triggered by starlight can all pump massive amounts of these gases into a planet's atmosphere. To truly find evidence of life, scientists must hunt for chemical disequilibrium, a state where the atmosphere contains a mixture of gases that should normally react with each other and disappear unless something active is constantly replenishing them. The core scientific problem is a game of molecular detection played across trillions of kilometers of empty space. It requires us to build instruments so sensitive that they can isolate a few single photons of light, filtering through a distant sky, separate that faint signal from the overwhelming roar of a blazing star, and then use rigorous mathematical models to prove whether those molecules are the result of dead rocks or the collective breath of a living biosphere. It is a task that pushes human engineering to its absolute limits, and the results are rewriting everything we know about our place in the universe. To appreciate the true scale of what has been discovered, we must look directly at the raw, verified data collected by the James Webb Space Telescope during its observations of the exoplanet designated K2-18b. B. This world is located approximately 120 light-years from Earth, positioned within the constellation Leo. It orbits a cool, dim M-dwarf star, which is more commonly known as a red dwarf. Thanks to years of precise measurements, astronomers have established the fundamental physical properties of this distant planet with exceptional accuracy. We know that K2-18b possesses a mass equivalent to roughly 8.6 times that of Earth, and its physical radius is approximately 2.6 times larger than our home planet. These specific dimensions place it securely within a fascinating demographic of planets called sub-Neptunes. These worlds are completely missing from our own solar system, yet they appear to be incredibly common throughout the wider Milky Way galaxy. The most revolutionary data regarding K2-18b involves the chemical composition of its sprawling atmosphere. When the planet passed in front of its red dwarf host star, the near-infrared imager and slitless spectrograph, along with the near-infrared spectrograph onboard the Space Telescope, captured the filtering starlight. By analyzing this light, astrophysicists successfully detected robust, definitive signatures of two major carbon-bearing molecules. These molecules are methane and carbon dioxide. The presence of these specific gases is not merely an interesting chemical detail. It tells us something fundamental about the planet's environment. The data revealed that the atmosphere is rich in hydrogen, and the simultaneous abundance of methane and carbon dioxide, paired with a noticeable depletion of ammonia, aligns perfectly with advanced theoretical models of a Haitian world. On a typical gas giant, ammonia should be a dominant feature of the sky. However, because ammonia dissolves incredibly well in liquid water, its dramatic absence strongly suggests that a massive, global liquid water ocean lies directly beneath the thick hydrogen envelope. However, the piece of evidence that has generated the most intense scientific debate involves a much fainter molecular signature. The initial analysis of the transmission spectrum revealed tentative, low-significance hints of a compound known as dimethyl sulfide. On Earth, this volatile sulfur-bearing molecule is predominantly produced by biological activity, specifically emitted by marine phytoplankton in our oceans. Because there are very few known ways to produce large amounts of dimethyl sulfide through non-living geological or chemical processes, finding it in an alien sky would be an extraordinary breakthrough. But it is crucial to understand the difference between a tentative hint and a verified discovery. In the official peer-reviewed publications, the research team explicitly stated that the signature of dimethyl sulfide is weak and remains buried deep within the background noise of the data. It does not represent a definitive, highly certain detection. To achieve absolute certainty, astronomers require multiple subsequent observation cycles to either confirm the signal or rule it out as a statistical fluke. Another critical piece of evidence involves the planet's thermal environment and its orbital dynamics. K2-18b completes one full orbit around its host star in just 33 Earth days. Because its red dwarf star is significantly smaller, cooler, and dimmer than our Sun, this close orbital distance places the planet directly within the stellar habitable zone. This is the orbital region where a planet receives a balanced amount of energy, allowing liquid water to potentially persist on its surface without freezing solid or boiling away into vapor. While some early reports claimed that the surface temperature was exactly 120 degrees Fahrenheit, the reality measured by science is more complex. The planet's calculated equilibrium temperature is actually quite cold, estimated to be around -3 degrees Fahrenheit. However, because the planet possesses a dense atmosphere rich in hydrogen, a powerful greenhouse effect could easily warm the environment beneath the clouds, potentially raising the temperature of the global ocean to a level where alien life could comfortably survive. By separating the sensationalized headlines from the actual peer-reviewed science, we find ourselves looking at a world that is genuinely extraordinary, yet still wrapped in deep mystery. We have verified proof of a planet 8.6 times more massive than Earth, wrapped in a hydrogen sky filled with methane and carbon dioxide, with strong indirect evidence of a global water ocean. The tantalizing whisper of a biological molecule remains an unconfirmed frontier, a scientific cliffhanger that requires more data, more patience, and more rigorous observation. This is the true nature of astrophysics. It is a discipline that does not rely on sudden, blind leaps of faith, but rather on the careful, methodical accumulation of verified evidence step by step across the vast distances of the cosmic dark. The ongoing investigation into K2-18b matters profoundly because it forces researchers to test old assumptions and completely refines our understanding of planetary habitability. For generations, the search for life in the universe was dominated by what can be called a terrestrial bias. We assumed that the only standard template for a living world was a rocky planet with a thin nitrogen and oxygen atmosphere, similar to Earth. When we designed space missions and automated algorithms to scan the stars, we purposefully looked for mirrors of our own home. But the verified data from the James Webb Space Telescope demonstrates that the universe may produce entirely different classes of habitable environments that have no counterpart in our solar system. By providing strong evidence for the existence of Haitian worlds, this discovery opens an entirely new research direction in astrobiology. If a planet that is 8.6 times more massive than Earth can support a global liquid water ocean beneath a thick hydrogen envelope, then the real estate for potential life in the galaxy expands exponentially. Hydrogen-rich atmospheres are significantly larger and more extended than thin, rocky atmospheres. Because they interact much more visibly with starlight, they are much easier for our instruments to detect and analyze across interstellar distances. This means that instead of struggling to observe tiny, hidden rocky worlds, astronomers can focus their efforts on these larger sub-Neptune planets, vastly increasing our chances of successfully identifying active atmospheric chemistry elsewhere in the Milky Way. Furthermore, this discovery directly challenges existing models of atmospheric evolution and chemistry. Finding a world with abundant methane and carbon dioxide, alongside a distinct depletion of ammonia, forces scientists to reconsider how planets cycle elements between their interiors, their oceans, and their skies. It provides a real-world laboratory to study chemical disequilibrium. In an ordinary lifeless environment, chemical reactions should eventually balance out into a predictable inert mixture of gases. But when we observe a sky that actively maintains an unbalance, it forces us to carefully untangle the complex boundaries between deep planetary geology, photochemistry, and potential biology. This rigorous process refines the mathematical models we use to define what constitutes a true, unambiguous biosignature. Finally, looking at K2-18b matters because it represents a critical milestone in humanity's technological evolution. It proves that our species has reached a level of engineering sophistication where we are no longer just guessing at the nature of distant stars. We are actively dissecting the raw light filtering through the skies of planets orbiting other suns over 100 light-years away. This research serves as a critical pathfinder for future flagship missions, such as the ground-based Extremely Large Telescope and the space-based Habitable Worlds Observatory. The lessons we learn today while analyzing the complex noisy data of K2-18b will directly inform how we build and calibrate the instruments of tomorrow. It moves humanity from an era of blind wondering into an era of precise, methodical exploration, setting the stage for a systematic survey of our entire cosmic neighborhood. The exploration of worlds like K2-18b is a single, illuminating chapter in a much larger cosmic narrative that spans the entire history of the universe. To truly appreciate why the search for atmospheric molecules on distant planets is so significant, we have to look back to the very beginning of time and space. In the earliest moments of the universe, shortly after the hot Big Bang, the cosmos was a remarkably simple place. It contained almost nothing but the absolute lightest chemical elements, hydrogen and helium. Along with a few microscopic traces of lithium, there were no solid rocks, no vast oceans, and no complex organic structures. The universe was an empty canvas of gas waiting for a mechanism to drive it toward complexity. That mechanism arrived with the birth of the very first stars. Inside the intense nuclear furnaces of these massive stellar bodies, simple hydrogen atoms were squeezed together under unimaginable pressures, forging heavier elements like carbon, nitrogen, and oxygen. When these primordial stars reached the end of their lives, they exploded in violent supernovas, scattering these newly created elements across the darkness of the galaxy. This recycled material gathered into vast, rotating clouds of interstellar dust and gas. Over billions of years, these clouds collapsed under their own gravity to form new generations of stars, surrounded by complex circumstellar debris disks. It is within these dusty, swirling rings that planetary architecture is born. As microscopic grains of dust and ice collide and stick together, they gradually build up into larger planetesimals, eventually forming planets that clear out vast paths in their orbital tracks. The elements forged inside the hearts of ancient stars become the rocks, the deep water oceans, and the sprawling atmospheres of new worlds. This means that every single molecule of methane, carbon dioxide, or water vapor we detect in a distant sky is a direct product of billions of years of stellar recycling. The chemical complexity we are observing across space is not a localized accident. It is a fundamental structural feature of our evolving universe. This larger cosmic story becomes even more profound when we look at the specific type of star that hosts K2-18b. Red dwarf stars are the most common type of star in the Milky Way galaxy, making up roughly 75% of the entire stellar population. They burn through their internal hydrogen fuel at an incredibly slow, conservative rate. While our own sun has a total lifespan of approximately 10 billion years and will eventually expand into a red giant that swallows the inner planets, red dwarf stars can continue to shine steadily for trillions of years. This incredible longevity provides an almost unfathomable timeline for planetary environments to remain stable. On Earth, complex multicellular life took nearly 4 billion years to emerge from simple single-celled organisms. In a red dwarf system, a planet could potentially maintain a liquid water ocean and a stable climate for periods of time that dwarf the current age of the universe. This longevity shifts our perspective on the history of life. It suggests that the cosmos may contain biospheres that have had trillions of years to adapt, evolve, and develop complexity, far outlasting the brief existence of our own solar system. When we place our modern space telescopes into the dark balance point of space, we are not merely performing cold, isolated chemistry experiments. We are tracing the long, unbroken path of cosmic evolution. We are looking at a universe that has spent billions of years organizing itself from a simple fog of hydrogen gas into a complex web of stars, planets, and molecules. By learning to decode the chemical fingerprints of alien skies, humanity is beginning to understand its true place within this vast structural tapestry. We are discovering that the ingredients for habitability are scattered abundantly across the cosmic dark, waiting for time, gravity, and starlight to weave them into a living universe. The journey to decode the atmosphere of K2-18b represents a defining moment in the history of human exploration. For centuries, we could do nothing but look up at the stars and wonder. Today, through the incredible engineering of the James Webb Space Telescope, we are actively listening to the faint chemical whispers of worlds over 100 light-years away. We are discovering a cosmos that is far richer, more diverse, and more unpredictable than our old terrestrial models ever led us to believe. The verified presence of methane and carbon dioxide, alongside the tantalizing, unconfirmed hint of biological chemistry, serves as a powerful reminder that we are standing at the absolute frontier of a new golden age of astronomy. As we look to the future, our understanding of these distant skies will only deepen. Every new observation cycle, every advanced space telescope currently on the drawing boards, and every breakthrough in computer modeling brings us closer to absolute clarity. We are methodically clearing away the fog of interstellar distance, transforming the deep void of space from an empty, silent landscape into a vibrant ecosystem of planetary possibilities. We are beginning to see that life may not be an isolated, miraculous accident on a single rocky planet, but a natural, inevitable expression of an evolving universe. If you enjoyed this deep dive into the real, verified science of our cosmos, please consider subscribing to the channel and liking this video. Your support helps us move past the sensationalized headlines and continue bringing you accurate, beautifully crafted stories from the absolute cutting edge of astrophysics and space exploration. What do you think about the mysteries of K2-18b? Do you believe that hydrogen-rich Haitian worlds are the place where we will finally find definitive proof of life beyond Earth? Or will our first breakthrough happen on a small, rocky twin of our own planet? Share your thoughts and questions in the comments section down below. Let us keep the conversation going as we look out toward the stars together. Thank you for watching, and stay curious.